Now, in the given situation, we have a 300 gram mass on the incline. X-axis here, Y-axis here, and the force of gravity on the object straight down. Now I've labeled some other stuff here because I immediately proceeded to the free body diagram for the object. Okay, and we see the gravitational force acting straight down, and we see that by effectively taking a vertical horizontal system and rotating it so that the x-axis is parallel to the incline, we've rotated clockwise 37 degrees. Okay, because the angle of the incline with horizontal is 37 degrees. When we rotate 37 degrees, well, let's look down here. Here we are with the vertical horizontal XY coordinate system with the gravitational force purely in the y direction, and the negative y-axis is down here. We rotate 37 degrees, the y-axis swings out 37 degrees. So you have a 37 degree angle down here. Now the other thing that I have to convince students of is that it's much easier to work with circular definition of trig functions than it is to keep worrying about whether this component is positive or that component is negative and getting all confused. Now you still want to worry about it, but the formalism that I recommend is that you measure the angle counterclockwise from the positive x-axis, okay? So that that 37 degree angle between the y-axis and the gravitational force, 37 degrees clockwise from the y-axis to the gravitational force, results in an angle from the positive x-axis of what? 90, 180, 270, plus 37 degrees. So now you have a 307 degree angle, and we'll see what good that is in just a second. Okay? Okay, now we want to find the components of the gravitational force in the x direction and in the y direction. We call that F grav x and F grav y, which I'll sometimes call F gravy. Okay, and those projections, we want to sketch it, we want to see where they are. You know, we do a projection back to the x-axis. There's our x gravitational force, x component of our gravitational force. And here's our y component of the gravitational force projecting back to the y-axis at a perpendicular. Now, I'm confident that you understand that, but make sure you see the whole picture, okay? Now, the force of gravity, and I don't have an arrow over this, so I'm talking about the magnitude of the force of gravity on a 300 gram object, is about 3 newtons. 2.94 if you want to split hairs. But I'm not interested in multiple decimal place precision. I'm interested in showing you the procedure you can modify to whatever degree of precision is required by whatever situation you might encounter. So, and many times I'm going to just use 10 meters per second squared, which is only 2% error for the gravitational acceleration. Okay? And that would give me 3 newtons. And I'm not going to discuss that. If you can't get from here to 3 newtons, you need some serious review. Okay. And if you do, by all means, please do it. I'm not saying that you're deficient. Well, yeah, actually you are deficient, but you know, it's an addressable deficiency. You just haven't spent enough time doing what you need to do. Okay. Oh, you've forgotten something. Okay. Angle, and I call this angle alpha to distinguish from the theta that I often use here, is 307 degrees. So what's the x component of the gravitational force? Well, it's just 3 newtons times the cosine of this angle. And you don't have to worry about whether it's positive or negative, because when you take the cosine of 307 degrees, you're going to get a positive or negative, and it'll be the right one. And you should understand trigonometric functions, functions of circular functions within the circular definition, within the context of the circular definition of the trig functions. But that works. And if you multiply 3 newtons times the cosine of 37 degrees, you're going to get something very close to 1.8 newtons. Okay? And then that's multiplied by the I vector. I multiplied it down here, but I didn't multiply it there. I've got an arrow over this. Okay, so I've got to express this as a vector. So now, F grav x is 1.8 newtons times I for this mass and this angle. And F grav y, well, you just multiply your 3 newtons by the sine of 307 degrees. And then as a y component, you multiply that by j. Well, you multiply by the sine of 307 degrees is negative, and you get negative 2.4 newtons times j. So now we have the vector 1.8 newtons times I, negative 2.4 newtons times j. And we see where they are in this picture. We also see where they'd be in this picture. I haven't labeled them down here. I just brought the labeling, excuse me, up to here. So now the question is, what's the acceleration? Okay, well, the acceleration in the x direction, in any direction, is just the net force in that direction divided by the mass. The component of the acceleration in the x direction then is the net x force divided by the mass. Now, the only force we have in this situation, as described in the problem statement, is this component of the force. So that's it. Okay? So we divide 1.8 newtons times I by 300 grams. Now somebody said, you can't do that. Well, yeah, I can. I get 0.06 newtons over gram. That's perfectly okay. Now, of course, if I want to communicate with the rest of the world, I want to express that as either dynes or, I'm sorry, I want to express that in either centimeters per second squared or meters per second squared, or at least some unit of acceleration. So naturally, I'm going to either change this 1.8 newtons to dynes, okay, and I would get what, 180,000, no, 1.8, yeah, 180,000 dynes, or I'd change that 300 grams to kilograms. That would be 0.3 kilograms. Well, I do the latter. 0.3 kilograms into 1.8 newtons is 6 meters per second squared, and I've still got my I vector. So now I know that in the absence of friction, okay, the absence of any other force, this thing is going to accelerate at 3 meters per second squared. Now, of course, in the real world, there will be other forces involved, and we've got to take those into consideration. This would be the ideal case: no friction, no air resistance, no other forces to worry about. Most of those other forces are going to tend to resist motion, or at least the ones that naturally occur rather than being imposed on the object are going to tend to resist motion, which is going to probably reduce our acceleration, but we deal with that later. And that's not difficult to deal with. You want to start by understanding this, understand why we set the coordinate system where we do, understand how we get these components, and then practice, do problems so that you have to retrieve this idea from memory and work with it. Now the y acceleration is what? Well, it's 0 because we're on the incline and y is perpendicular to the incline. There's no motion perpendicular to incline, so there's no change in velocity perpendicular to the incline, so there's no acceleration perpendicular to the incline.